Thank you, François. This talk is going to be a little bit different from some of the ones that came earlier today. It's, first of all, a computational study. And my group and I, we've been studying quantum Hall systems for some years now. And so our foray into many-body localization was something we started about 2 years ago. It started with my postdoc, Scott Geretz, and then followed up with my students, Akshay Krishna and Matteo Ippoliti. And these are sort of canonical pictures that you'll see in the slides that follow. So I'm trying to address this talk to students and start from the very beginning, 70 years ago, or 60 years ago, I guess. So the first thing I want to try and give is a very lightning review leading up to many-body localization and the physics of disorder that preceded it. The second ingredient of this talk is the quantum Hall platform, which is the platform of two-dimensional electrons in a very large magnetic field, where you see an exquisite phase diagram, which I'll just flash and just introduce people to this system. And then we'll come to the main part of the talk, which is basically trying to ask the question whether many-body localization can be studied in the quantum Hall regime. And so the first introduction, I'll briefly talk about single particle localization, then talk about spin localization, and then very quickly flash 2 slides of the early work on many-body localization, the Basco-Alainer Altshuler work, as well as the work on the random transverse field spin half chain. And our technique to understand many-body localization will be eigenvalue spacing statistics. And in that sense, I will introduce that right here and hopefully get the message across as to how we are actually going to look at and identify many-body localization. And I'll summarize with some conclusions and outlook. This is a very old slide, as you can see it from the transparency days, which it's the whole subject of disordered systems started with Anderson's paper on absence of diffusion in certain random lattices. Anderson was actually interested in the question of spin diffusion, but he found that it was easier to solve the problem of single particle electrons, fermions, hopping on a lattice. In this case, just imagine you have a 3-dimensional simple cubic lattice with a density of states that is well known with its Van Hove singularities, and a nearest neighbor hopping. The twist that Anderson gave was this epsilon, the on-site energy on the various lattice sites was taken to be disordered and probability independently distributed according to this distribution that's known as the box distribution for obvious reasons. And what you find when you do this is that when you have, starting from the clean system where all eigenstates are extended, when you put in some moderate disorder, you start seeing localization, that is eigenstates that are no longer covering the entire sample, but are localized around certain specific sites. And that this happens towards the end of the, in the tail states, and eventually, when W is large enough, the entire band gets localized. There are no more extended states in the system. And there's been a lot of numerical work on this. This is data from McKinnon and Kramer's review article, also a few decades ago, where they plotted the disorder in this axis and the energy in this axis. So this number 6 is basically the undisordered lattice, and these are all extended states, and they persist for some disorder. But eventually, by the time you get to a number which happens to be, for the box distribution, something around 16.5, all states get localized. So everywhere outside of this line, states are localized. And that's my very quick review of Anderson localization. One aspect that we will use of the Anderson localization problem is you can look at the eigenvalue distribution. You just diagonalize the matrix on any given size, large enough so that you get start seeing the thermodynamic limit. And what you find is if you define the adjacent eigenvalues splittings as delta I, then delta I are distributed according to because the disorder is random. And what you find is that if you are in the localized state, then because typically consecutive eigenstates are very far away in phase, in real space, there's no mixing between them, and therefore you get just random numbers, which is Poisson statistic. That's that black curve. But as the states get extended, depending on the symmetry of the Hamiltonian, in Anderson's case, it's orthogonal, you get a curve that looks like the blue curve, or else you get the particular case we'll be interested in is the complex Hermitian case, because we're talking about electrons in a magnetic field which have phases, and so you get the red curve. And so you can see that the eigenvalue distribution is quite different. There is a hole at low eigenvalue separations. The solid line is something that was Wigner surmised, which is the exact result for 2 by 2 matrices, and the dots are numerics for a larger number of sizes. 20 years later, it turned out that there were one of the systems in which the metal insulator transition was studied was doped semiconductors. And what you found was while the conductivity was reasonably well described by field theories based on Anderson's model, what you found was that the magnetic properties were completely not given by that. So in particular, what you find is, what I'm plotting here is the susceptibility, magnetic susceptibility of this system as a function of temperature. And notice this is a log-log scale. And what you find in the insulator is that you find a susceptibility that's diverging as a power law. This power law is roughly around 0.6, if you look at the slope of this line, 0.6, 0.7. And these numbers are actually the density of these dopants relative to the critical density at which the system goes from being insulating to metallic. So this sample is insulating, these two samples are metallic. And what you find is the susceptibility at low temperatures actually doesn't seem to care whether the sample is metallic or whether it's insulating. Does not have a Pauli susceptibility as Ashcroft and Mermin would have you believe. Okay? It actually is divergent in the metal. And this turns out to be because of rare fluctuation effects. And you find that you get spin localization even in the metallic phase. This was work that I had done with Patrick Lee and then later with Daniel Fisher. This data is from the Cornell group on phosphorus and boron doped silicon. This was something else that was very interesting. Here you have spin localization, even though the charge is not localized. Finally, we come to the big picture, which is what Anderson was really after. And the first attempt at that was from Basko, Lehner, and Altschuler. What they showed was that in an isolated many electron system, if you start from the Anderson localized state, that is, you start somewhere here, very large disorder, and then put in interactions perturbatively, they got this amazing result that the conductivity is 0 for below a certain temperature and is non-zero for higher temperature. So you have an insulator to metal transition at finite temperature, which they interpreted as an Anderson-like localization of many-body wave functions in Fock space. But this was a perturbative analysis, and the next step that in terms of trying to understand many-body localization from a sort of a statistical physics point of view and its connection to eigenvalue thermalization hypotheses was work by David Hughes and co-workers. And so I'm showing you data from David Hughes and Arijit Pal, his graduate student from 2010, about 9 years ago. And what they studied was the random field spin half chain in which spins are, nearest neighbor spins are coupled by an exchange interaction J, and there is an on-site field at each site, which is a random variable, and again, uniformly distributed according to the box distribution. And what they did was they tried to look at the scaling with size and randomness, that is H, this quantity H here, of the ratio of adjacent gaps. So they looked at 3 eigenvalues, looked at the 2 gaps from the 3 consecutive eigenvalues, and made a ratio of the minimum to the maximum. This turns out to be a very convenient quantity, dimensionless quantity that you can look at. And depending on whether you have Gaussian orthogonal ensemble or Poisson statistics, this number should be 0.535 or 0.385. And so what they actually saw was, for all the sizes that they could do, was that for small h, they got Gaussian GOE values, whereas sample averaging, of course. And for large disorder, they found Poisson statistics. And all these curves seem to cross at roughly at some value of h, and suggesting that there was a transition from an extended state to a localized state. Now, this is a one-dimensional model of spins, and there are many questions that obviously one has. What happens in higher dimensions? For example, our chair and co-workers have pointed out to the fact that rare fluctuation effects actually destroy many-body localization in higher dimensions. On the other hand, that may happen at timescales that are not particularly relevant to some of the experiments, so one may still want to understand whether there's an approximate many-body localization at short lengths and experimental timescales. Of course, the big problem numerically is that when you do one-dimensional models and you do spin models, the reason why Pal and Hughes did spin model was because the local Hilbert space has just 2 states, and if they have a length L, it goes as 2 to the L for a size L chain. And that's exponential in the size, but nevertheless, it's the smallest that you can almost imagine. If you were instead doing a fermionic model, like a disordered Hubbard model, you would find that you would get 4 possible, no electron, 1 electron with spin up, another one, or with spin down, or 2 electrons with spin up and spin down. So it'll go as 4 to the L, which is the square in terms of the Hilbert space, and that's a problem when you're trying to do numerics, because your Hamiltonian just becomes too big. So that is what brought us to the quantum Hall platform. In quantum Hall physics, what happens, you have electrons in 2 dimensions, subject to a very large magnetic field. Because they are subject to a large magnetic field, the electron levels, the single particle levels, are Landau quantized. So you have automatic quantization, and you can, by suitably increasing the magnetic field, get all your electrons into the lowest Landau level. Furthermore, they are spin polarized also. So the spin degree of freedom is gone. So in some sense, this is the charge analog of the spin chain, because you can have, they are not site, this thing, they are Landau level wave functions, but you could either occupy them or not occupy them. So there are 2 states, or a single particle orbital. So it's, in that sense, very similar. Of course, the difference is that this is in 2 dimensions, not in 1 dimension. So let me give you a lightning review of the quantum Hall physics. So here is a 2-dimensional caricature of a 2-dimensional electron gas that is actually formed between 2 semiconductor aluminum gallium arsenide structures in between. There's gallium arsenide where the electrons reside. The dopants that provide the electrons can be made as far away from the electron gas, so effectively have very little disorder. You can control the disorder, basically. And in such a case, if you have some disorder and pass a current in 2 dimensions, in a magnetic field, you find you get a transverse voltage, and the resistance, the Hall resistance, which is the ratio of the transverse voltage to the current, has this staircase-like structure as a function of magnetic field. And it turns out that these resistance values are exactly quantized in h over an integer time e squared if your sample is not too clean. And that's what you see here. This corresponds to integer h over n e squared, where n equals 1, n equals 2, n equals 3, 4, and these are quantized to 1 part in 10 to the 10 and used as standard along with atomic clocks to define all the various fundamental constants of nature. And the picture very much is that as a function of energy, the density of electrons is continuous for zero field, but as you put on a field, you get a bunch of Landau levels. These are harmonic oscillator states, which are separated by an energy which is proportional to the magnetic field, so you can make this as big as you like. The number of states is also proportional to the magnetic field, so you can get all these electrons into just one level if you make the magnetic field large enough. So we will actually concentrate actually to the magnetic field limit where all the electrons are in the lowest Landau level. I haven't shown the spin splitting, but there's also a spin splitting. That's just more of a caricature. This is the orbital Landau quantization. And of course, this particular system actually has a much richer phase diagram as you make it very clean. It has not only the integer quantum Hall effect where the longitudinal resistance goes to 0, but it also has fractional quantum Hall effect, say like at 1/3 where it goes to 0, and there's a whole series of possible quantum Hall phases which are marked by plateaus in the Hall resistance and zeros of the longitudinal resistance. These have been understood through the work of Laughlin, Haldane, Jane, and others. As it turns out, we are going to make this sample, this whole picture sort of irrelevant for us. We are going to be in the regime where the filling is less than 1, so it's on the right side of this middle point here. But we'll put in enough disorder that all this nice phase diagram completely washes out. So this is not relevant to today's talk. But it's nevertheless amazing that with one tuning knob magnetic field, you can get all these rich phases one after the other, where you see integer, fractional, you get crystalline striped phases, you get topological excitations, you get this quasi-particles that are very that are composite fermions or composite bosons, depending on what field theory you like to use. So it's a very rich subject, but that's not the topic of today's talk. What we want to do is have electrons in the lowest Landau level. So the first study that was done with Scott Jarrett's was we solved the problem of 2D electrons in a perpendicular magnetic field, take the large field limit, so all the electrons are in the lowest Landau level, and that's LLL, as I call it. We will then add Coulomb interactions between electrons and white noise disorder potential with a strength W relative to the strength of the electron-electron interactions. And we solve the many-body problem for small finite sizes. The Hilbert space has the number of Landau orbitals that are there in a finite size is proportional to the area. So if the area is small, it's proportional to that, and we can make it so that there are 10, 20, 30 Landau orbitals in one given Landau level. And we will use the geometry of a square torus. That is, we take a square two-dimensional sheet and put periodic boundary conditions. And finally, we'll use precisely the same thing that Paul and Hughes used. That is, we look at the level statistic of the many-body eigenvalues. And in particular, this ratio of the minimum gap of 3 consecutive eigenvalues to the maximum gap. And this number for the Gaussian unitary ensemble is close to 0.6, and for the Poisson, it's 0.386. And it's easy to understand why this number is smaller for the latter, because eigenvalues don't repel in the case of Poisson, whereas in the Gaussian unitary ensemble, their eigenvalues repel because they talk to each other being delocalized. Yeah. You get, well, okay, so you get a crossover from this to this because Poisson is way in the tail of the states, if the localization length is much smaller than the size of your system. But it turns out that there is always a delocalized energy at the center of the band. So you get GUE in the center of the band. So if you take a small size system, the kind that we are taking, you're going to get GUE almost all over because they talk to each other. They are pretty extended. Without the field, it is localized, yes, of course. In 2 dimensions, with any disorder will localize. And the kind of disorder we are putting in, it would be very localized at very short distance of the order of the inter-electronic separation. With a magnetic field. But without interactions, yes, yes. In fact, that turns out to be the biggest effect that we see. You'll see that from. It was sort of supposed to be my punchline, but you guys took it away in the early. That's fine. So what we found, what Scott found was that as you increase the disorder, and notice this disorder is on a log scale, covering several orders of magnitude. Okay? We're starting with disorder that's of the order of order 1, and we're going up to 10 to the 4. And these are different sizes, and one other thing that we can vary is we can vary the filling in the Landau level. So whether we have a filling factor of 1/3, that is the number of eigenstates in the Landau level is 3 times the number of electrons, or it is 2 times the number of electron, we can vary that. And what is shown here is basically for 1/3 filling. That is, we have 3 times as many electronic states as there are electrons in the system. And what we find is that for small disorder, we always get the GUE result. For large disorder, we always get the Poisson result. But as a function of size, the size is proportional to the number of electrons that we have. So in this case, there's 18 flux quanta. In this case, there's 36 flux quanta. What you find is the curves shift quite a bit to larger disorder. If we take the midpoint, for example, and plot how what we call the critical disorder changes with size, we find that it is scaling as some 4th or 5th power of the size, linear dimension of the system. It is moving out to large values of W very, very fast. And if I were just to sort of say that, well, this is going to continue for larger sizes, it's consistent with the fact that there is no many-body localization transition in this model in the thermodynamic limit, because this is going to go there, and we at 10 to the 25 or whatever it is. If we could do bigger sizes, of course we can't, because the Hilbert space is so much bigger, going exponentially with the size. But it's a very rapid motion with size. There was a paper by Nandkishore and Potter that tried to make this case. They basically made the argument that because the states in the center of the band are delocalized, that gives rise to long-range power law kind of hopping, and as a result, this system should not show many body localization. But if we put in the numbers using their argument, we would expect that our small sizes should show a critical W, or that should scale as the 0.4 power of the length. What we are finding is 4, roughly 10 times what comes from the Potter, Nankishore-Potter argument. So there's something else also going on. This system just does not want to many body localize. So the question that we got, we then went to, is it topology or 2 dimensions? That's really important, and this was answered in these 2 papers to the best that we could do in terms of numerics. So the first thing that one can think of is you can add a periodic potential to the system. And then you get what's known as the Hofstadter problem, and then you go to the high field limit and you end up with Landau levels. So if you put the period of your potential and the filling just right, what turns out is you can manage to get 2 subbands from 1 Landau level. And these subbands are actually very flat. They look not flat because we have enhanced this by a factor of 10 to the 4. The gap between these 2 bands is 8700, and the bandwidth is 1. So if I were redrawing the picture, I would make that 1 and that 10 to the minus 4. So you get 2 bands that are basically roughly the same in size, but the only difference is this band has a topological churn number that's given by 1, which is the same as that of the Landau level, where this is a topologically trivial band with no churn number. And the way we are able to do that is just via Fourier coefficients of the potential, and this is sort of an equipotential plot of what we have. So if topology was not important, we would expect that these 2 subbands would have very similar response. So what we found, we did the same thing with these 2 subbands as a function of disorder, again on a log plot. And what you find is, again, both bands start with GUE at small disorder. They go to Poisson at large disorder. And this, by the way, is 1-dimensional scaling. That is, we take a fixed width and just increase the size of the system in 1 dimension. So this is the equivalent to a 1-dimensional chain problem. And what we find is that there is a clear crossing that we can see when you're looking at the churn 0 band. But if you look at the churn 1 band, the crossing is moved to much larger values. And if you look at each individual curve for each size, you'll see that these curves are shifted quite a bit to the right compared to the ones for the churn 0 band. So it's telling you very clearly that the topology, which is guaranteeing a critical energy at the center of the band, even for these small sizes, has a very drastic effect on where the system goes from being extended to being quasi-localized. And again, this one, if we look at the midpoint and scale it with the number, what you find is, again, it's going up to, even though it's not going quite as fast as the simple Landau level, it's certainly going faster and faster as the size goes up. On the other hand, if you look at the 0 churn band, what we find the midpoint is actually seems to be saturating, which is consistent also with getting us a crossing point. So this would suggest that as far as the 1-dimensional problem, charge problem is concerned, you get MBL if the band is not topological. Now, unfortunately, when you try and do the thing for the 2-dimensional scaling, things get a little bit complicated. I'll show this data, and then we'll. What you see is, again, that the churn 1 band is extremely seems to be very clearly trying to delocalize as much as it can, whereas the churn 0 band is, the midpoints are well below this number. It's more here, which is like there. And again, if I naively just take the midpoint and look at how it scales with the number of flux quanta, one is headed to infinity, the other one looks like it is getting. So again, the answer is significant difference between churn 0 and churn 1 bands. But if you look at the crossing here, you find that it's, even for the 0 churn band, the crossing is moving with size. So it's not clear, someone who is very critical might say, well, maybe it just moves off to infinity when you go to infinity. And here, who knows what's going on. So there's another issue, which is that because of the discreteness of lattice sizes, we cannot, for a given fraction filling of electrons, do all lattice sizes. So we have to interpolate between different lattice sizes to get data. So there's that additional complication that comes about. So we did a completely different model, which is basically take a Landau level and add delta function impurities randomly to the Landau model. Now, it turns out that when you take either an attractive or a repulsive point like delta function impurity, what happens is that it pulls out a bound state. So here's the case of an attractive. Here's the energy versus, and this is the Landau level, lowest Landau level. If you put in one delta function impurity, it pulls out one bound state here. And then if you put a whole ensemble of them, it turns out that each impurity pulls out one. And this creates an impurity band, which is dispersive, but not very dispersive. It turns out that this bandwidth is less than 1/10 of the energy. So again, we are in a regime where this is relatively a flat band, not as flat as we can do in the Hofstadter problem, but flat enough. And we can then compare this band and that band. This is essentially the Landau level, basically. The reason why these states are not perturbed is because wherever you put your impurity, you can make your wave function vanish at the impurity. So they are completely unperturbed. This is something that was shown by Brezin, Gross, and Itzek in 1980. The big advantage of this is that because this is a random impurity configuration, there's no lattice commensuration issues whatsoever. The price you have to pay is you have to do ensemble average over these random impurity configurations. So you have to do a lot more samples, but you can do all sizes. The only thing that is commensurate is the number of electrons that are there in the system. That's the only, which is exactly what you have in one-dimensional systems. So here we are managing to get a two-dimensional system which has the same sort of quantization of sizes as in one dimension. And I think one can do the same thing in spin systems. It's just that people don't think about spins on a random graph rather than on a lattice. So we did the one-dimensional scaling for this model, and there is very clear that the impurity band has a crossing and a many-body localized phase. Then we did the two-dimensional scaling. So this, notice that this was pretty unclear in the Hofstadter model, but in this model there is absolutely no doubt that there is a clear crossing for all the sizes. Then we did the two-dimensional scaling, and these are the results. Notice we have really expanded this curve. Okay, these are curves that is 2 orders of magnitude expanded compared to the curves I was showing you before, and because we have accuracy to talk about these kinds of numbers. And what you find is that the crossing point seems to be drifting to the right as you go to bigger sizes. So unfortunately, it looks like we are not able to say for sure whether the limit is finite or the limit is infinite. We need more sizes. That's how the situation is in 2 dimensions. But it does seem, this is all for the churn 0 band, that is the impurity states. The churn 1 band, there's no question that it does not show many-body localization. We tried one more attempt at the lattice model. We looked at charge imbalance, and what we found again was that if you look at the 0 churn band, the imbalance remains at large disorder, almost 100%, whereas the churn 1 band has much less imbalance. And if you make this critical W from the midpoint, either of these curves or these curves, they show the same kind of behavior, whether you look at the R statistic or you look at the charge imbalance. So that in the last 12 seconds that I have, I'd like to make some concluding remarks. There are some general remarks that MBL is a frontier topic and which derives its inspiration from the Anderson localization, but has far-reaching consequences, not quite envisaged at that time. It comes with the destruction of the eigenstate thermalization hypothesis. They don't thermalize and retain memory of their initial state. MBL seems established for spin chains in transverse field, not clear for higher dimensions. And the numerical methods, of course, always face this exploding problem of Hilbert size space going exponentially with system length. And the best chance is, of course, for models with the lowest size per unit. That's two either spins or electrons in a high magnetic field. So in the strong perpendicular, the strength, that's another platform which I hoped I try to convince you that that's the next platform worth doing. It's a continuum model, so it's not limited to lattices. It allows exploration of interplay of topology and many-body localization. A third thing is that it also has a further knob of filling, Landau level filling, so you can look at it for many filling factors. The limitations is the Hamiltonian matrix is denser than spin models with local interactions. So that's the price you have to pay to do this. In terms of results, the topology definitely has a clear result. Non-topological bands can be many-body localized. Topological bands resist many-body localization very, very strongly. So they don't, as far as I know, nobody has been able to get them to localize. For one-dimensional scaling, it's robust for both the impurity band and the Hofstadter model, but it's much less for topological bands. And for two-dimensional scaling, it's found to occur in non-topological band, though it's not fully clear if it survives the thermodynamic limit because the crossing point was moving with size. Certainly, topological bands in 2 dimensions do not seem to support. So with that, I'll stop. Let me give credit to where it's due. Scott, Akshay, and Matteo.
Thank you very much. Yes. Several questions. So one, did I understand correctly that the interaction was the real Coulomb, 1 over R?
Yeah, interaction was 1 over R Coulomb.
Because with in 2 dimensions with 1 over R interaction,
yes.
So we know that the many-body localization is destroyed even in the if everything else is most conventional, yeah. So
and on these sizes,
and it's destroyed in a kind of in a power law fashion, not just by some exponentially rare events. That's not what I mean, but it's destroyed in a power law fashion, and that's what is also seen in well, in 2D it's more difficult, but you can do analogous numerics with 1D and adjust the corresponding power law, and this is what's very nicely seen. So then there would be one, in addition to the fact that you have this quantum Hall situation with divergent localization length at somewhere, then there is which is one more mechanism for power law destruction of localization. There is also this with power law interaction.
Yeah. No, well, if I were to interpret our data in that format, it says that the topology matters a lot more than the interaction length. Of course, you have to realize that the sizes we do are really small. So whether the interaction is power law or whether it is exponential or it's we could do the same things with Haldane pseudopotential, for example, which would be basically the short range part of the interaction. But my gut feeling is it would not change our results. But that's something that's a good suggestion. We should repeat the calculation with short range interaction and see whether there are any significant differences.
Okay, so another comment is even if there is everything is many-body localized for such small systems, you always see some considerable drift to the right of all these curves because the crossing point eventually will become Poisson, and so that's at criticality. And so you should discriminate now between the drift that you would have the part which is due to already in the many-body localizer situation, the part due to power law interaction, and then one which is due to this divergence of the localization length.
Well, that would,
and if something else, yeah. So concerning topology, now I have a question. So what does it mean that you have topology? So you have disorder, yeah?
Yes.
So are your state exponentially localized? Are you?
In the Chern 0 band, they are exponentially localized. In the Chern 1 band, they are exponentially localized, but their localization length diverges at a critical point in the
one energy,
in the band. Yeah.
Okay, yeah.
So that is
then there is this mechanism that you mentioned that was by Nankishore
and Potter, but we think it's that there are more, it's a stronger divergence than what they get.
Yeah, but maybe that's because now the various reasons combine as power law interaction.
We certainly, your point is well taken that we should repeat the calculation with short range interaction.
Some other question, remark? Thank you very much.
Thank you.